Our previous video was on database. Now let us move on to geometric model, under which we have overview of geometry, basic concepts and definitions, creating geometry, working with imported CAD models, and checking the geometry. Overview of geometry. Computer models for geometry serve many purposes. CAD geometry models can serve as blueprints for manufacturing, a source for technical illustrations, and a source for parts procurement. By comparison, the geometry modeling capabilities in Patran are directly towards creating a complete finite element analysis model. This finite element analysis model will eventually include a finite element representation of the geometry and assignments of loads, boundary conditions, material properties, and element properties. The complete finite element model is what your analysis program eventually sees as input data. Options for starting the geometry model. Patran provides a various variety of options for creating, modifying, and qualifying a geometry model. You may start your model in one of three ways. Select the geometry application on the Patran main form. When chose from over 130, create, transform, and edit actions as a geometry form to create new structures. Import models created in the CAD system into Patran using the File or Import menu option, then edit them. Copy an existing Patran model database and use the existing model as the basis of your new model. Model building tasks. Patran maintains complete accuracy of the original geometry, whether it comes from a separate CAD part file or from within Patran. Regardless of how you start the model, geometric application form provides numerous options for editing, managing, updating, and verifying the entities in your model. There is also flexibility in the sequence of geometry and meshing. Typically, you complete the entire geometry model first before moving on to the finite element meshing application. However, you may also complete the geometry, then mesh your model one portion at a time. Basic concepts and definitions. The topic in this session describes several key concepts within Patran geometry. It will be helpful to you to understand these concepts before you start building a geometric model. Parametric space. Patran utilizes the concept of a parametric space for simpler and more efficient internal computation. In parametric space, a curve is defined in terms of only one parametric axis, that is x1. A surface is defined in terms of two axes, x1 and x2, and a solid is defined in terms of x1, x2, and x3 parametric axes. Any object has a size of exactly 1 on each parametric axis for which it is defined. Therefore, coordinates along these axes always ranges in the value between 0 to 1. Patran's mapping functions translate between parametric and the XYZ space. For each curve, surface, or solid that you construct in Patran, the software derives a unique mapping function f that can translate between the object set of parametric coordinates and its more standard three-dimensional XYZ coordinates as shown in the Patran viewport. The following illustration compares how a surface would look in parametric space with a realistic rendering in the viewport's three-dimensional XYZ space. Connectivity. Connectivity is located and orientation of the parametric axis. The parametric axis x1, x2, and x3 have a unique orientation and location on each curved surface and solid. For example, the following two surfaces are identical but their connectivity are different. For a curve, there are two possible connectivity definitions. For a four-sided surface, there are a total of 8 possible connectivity definitions. For a triparametric solid with 6 faces, there are a total of 24 possibility connectivity definitions in Patran, 3 orientation at each of the 8 vertices. Geometric entities. This session provides a detailed look at the characteristics of the geometric entities that you may select as building blocks like point, curve, surface, and solid. The following additional entities serve as a frame for references for geometric constructions rather than building blocks like plane, vector, and plane coordinate. Points. In Patran, all points are non-parameterized dimensionless coordinate locations in three-dimensional XYZ space. You may use points by themselves to create point elements such as masses and to construct higher-level geometric entities. Curves. A curve has one parametric dimension in space. You can subdivide a curve into 1D elements such as truss or beam element and can use them in geometry construction. A curve has one parametric variable used to describe the location of any given point P along a curve as shown below. Surface. Simple surfaces are regular 3 or 4-sided. In terms of parameterization, simple surfaces are two-dimensional points set in three-dimensional global XYZ space. Any given point P on the surface can be located on the coordinate. General surfaces can include more than 4 edges as well as interior holes or outcuts. Each trimmed surface has an invisible associated parent surface that defines its parameterization and curvature. There are several types of general surfaces. Trimmed surfaces may be either planar or 3D. Composite surfaces merge a collection of surfaces into one entity defined within a specific boundary. Solid. Patran supports a tri-parametric solids and a general boundaries representation solids. Solids have more than 4 to 5 surfaces with no interior voids or holes. Most solids created with the geometric application are tri-parametric. In terms of parameterization, each solid is a 3D point set in global XYZ space. For any given point in solid P can be located by the 3 coordinate and whose value ranges between 0 and 1. General boundary representation are formed from an arbitrary number of surfaces that define a completely closed volume. B-rep, that is boundary representation, solid can be included interior of voids or holes. Planes and vectors. Vectors and planes serves as useful entities for constructing geometric models. Vectors define an origin and an endpoint for use in modeling operations such as translating geometry or construction geometry between the 2 points. You may create vector in Patran using numerous create vector options. Planes are particularly used in symmetric operations such as creating a mirror image of geometry components. Patran provides numerous create plane options. Coordinate system and frames. Coordinate system defines a coordinate frame of reference used in modeling operations. Patran automatically defines a global rectangular Cartesian coordinate system in each database. The system origin 0 is indicated by a white plus sign in the viewport. The global axis in the lower left of the viewport indicates the current orientation of the global coordinate system. The geometric options create coordinates along U to create 3 types of local coordinate system. The first one is rectangular or Cartesian system which have 3 orthogonal axes in rectangular space. The second one is a cylindrical system with axes in a radial, angular and depth dimensions of a cylinder. Third one is spherical system described in terms of radius and 2 principal angles. Using geometry application form. To use the geometry application form, click on the geometry button on the Patran main form. The geometry application form will appear on the screen. Select the action object method combination from the drop-down menu at the top of the geometric application form. Several additional form fields display on the lower 2/3 of the geometry form that vary depending on your selections for action object and method. Action. Action defines what you want to do. Action falls into 3 categories: create, modify and verify. The table that follows briefly describes the action choice of the geometric application. Please pause the video and have a glance. The object field defines the type of geometry. For example, if you specify a create action, the object defines what type of geometry you want to create. Pause the video and have a glance at the table. Working with imported CAD models. In some cases, you can use imported CAD geometry without modification. However, models are not always prepared in CAD systems with the ability to analyze them in mind. It is common to modify imported geometry to remove extraneous detail and to construct missing surfaces needed for topological congruency. Some of the most common problems with imported CAD data and suggested solution with Patran are as follows. Remove excess details. Plan ahead in your CAD modeling and use layers and do not color to separate out entities that you want to include from the analysis module. Use filters options to restrict input to surface types of entities. For example, bring in solid only or curves only to rebuild the model in Patran. The filtering options are found on the subordinate form nested under the import file. Use imported CAD geometry as a base to construct simpler and analysis geometry in Patran. Here the vertices, curves and bounding surfaces of the original CAD model are used as a basis of construction geometry using features available in Patran geometry menu option. There may be cases where a large surface or solid is represented by several smaller regions, adding to its complexity. You can select Create Surface Trimmed and Create B-Rep to simplify complex geometry by chasing it on outside edges or faces. Alternatively, in the case of many adjacent entities, consider approaches for merging adjacent surfaces such as Action, Create Surface, Composite, or other construction method. Whichever approach you choose, a certain amount of simplification can have a major impact on both the time spent generating a finite element mesh and computing time required for running an analysis. And missing surfaces. For some cases where a regular number of edges, for example 3 or 4, will enclose the region, select the geometry action such as Create Surface Edge to fill in missing surfaces by specifying the edge of adjacent surface. When a region is bounded by more than 4 sides, select the geometry action Create Surface Trimmed. In this case, you may first create a composite curve representing the exterior boundary using either the Create Curve Chain option or the Auto Chain button on this Create Surface Trimmed form. An alternative to this is to break the region into several simple biparametric surfaces. Repair incomplete entities. Popular CAD data formats such as the popular IGES format are often extremely broad standard and include many different types of geometric data. IGES is a very rich standard and not all entities types in IGES are supported by every CAD system. Ensuring topological congruency. To be topologically congruent, your model must meet the following requirement. Adjacent region of geometric share matching boundaries the vertices. The geometric component form a closed surface or solid region. There is no overlapping between the adjacent region. Finding incongruency. The geometry form selections, verify surface boundary and verify solid B-rep help you to locate areas of your model that are topological incongruent. The update graphics form appears after you press apply on the geometry form. This form allows you to plot incongruent surfaces within a model. Correcting incongruencies. To make the surface congruent, choose the following actions. Create surface and match or edit surface and match. Avoiding small angles at surface corner. Try to keep the inside corner of surface to 45 degree or more. The reason is that when you mesh surfaces with quadrilateral elements, the shape of the element are determined by the overall shape of the surface. The more skewed the quadrilateral elements are, the less reasonable your analysis result may be. Verifying and aligning surface normals. The direction of the out of the plane normal vector of a surface is an important consideration for applying analysis data such as loads, boundary condition and element properties. Use the geometry applications edit surface reverse form to display the surface normal vectors and to reverse or align the normals for a group of surface. You can also verify normals indirectly while constructing a surface by displaying the parametric directions of the surface. Now that we come to the end of this session, let us move on to finite element meshing in the next course.